All right, everybody. Today we're going to talk about infinite series and the ratio test, which is our first test. It's our first test for series convergence. Okay, so below in black and red, I have two different series written. One of them is an infinite series, and the other one is a partial sum. All right, so here I have a partial sum in red. That would just be the sum of the first four terms. And next to it, I have an infinite series, which is looking for the sum of all terms forever. So basically, it's just asking for what is that sum going to be potentially convergent to. And we're going to use the ratio test today on a few different examples to figure out whether or not a infinite series will converge. Now, the ratio test does not give us the value it converges to. It just answers this question, yes or no, convergent or not. All right, and so we'll get three different possible outcomes. It'll either say yes, convergent, no, not convergent, therefore divergent, or inconclusive, right? So just to lay a couple of these out, this is how we would start the first, let's say, 3 or 4 terms of each of these. This would be 4 times 2/3 to the first, plus 4 times 2/3 to the second, plus 4 times 2/3 to the third, on forever. Okay, the second one would be n factorial, which would be 1 factorial over 2 to the first, plus 2 factorial over 2 to the second, plus 2 factorial over 2 to the third, plus, oops, I'm sorry, that should be 3 factorial, sorry. Should be 3 factorial. 3 factorial times over 2 to the third, plus 4 factorial over 2 to the fourth. And we could actually potentially find out that sum, seeing that it is a partial sum, not an infinite sum. Today we're going to learn using the ratio test whether or not that sum will converge. Okay, so just one of the things you want to think about as you're thinking about convergent series is the first thing you want to look at is it geometric? Then you don't have to use any of these 10 convergence tests that we're about to embark upon, the first of which is the ratio test. So is it geometric, right? If it's geometric and r is less than, the absolute value of r is less than 1, right, our common ratio, then it will converge. It will converge. All right, so in this case up here, it's geometric, right? We're going to be multiplying, it looks like, by 2/3 each time. So our first term and our common ratio allow us to find the actual sum to infinity. That's something we can get into. There's a homework problem similar to that. So I'm going to get into the ratio test and what's called the divergence test first. Okay, so here's an infinite series. All right, let u1, u2, and u3 be an infinite sequence, right? Just an infinite list of numbers. We can form a new sequence by taking each of the partial sums and letting S1 equal U1, S2 equal U1 plus U2, and S of n equal the sum of all terms. So basically, as we send n to infinity, we end up taking I from 1 to infinity, and therefore it becomes an infinite sum. But that only happens if we take the limit as n goes to infinity. Okay, so the value S of n, which is the sum of the first n terms, is called the nth partial sum. And like this says right here, if we take the limit as n goes to infinity, that becomes the infinite series. And it's either convergent or it's divergent. So we're going to look at how we can analyze which one is which. I'm going to skip this example 24. I don't find it all that useful right now. I'm going to move on to how the divergence test comes out of this. Okay, so it's important, right, that we find out whether or not the series as n goes to infinity is convergent. Therefore, we've got some work to do here, a couple of properties that come from it, very similar to limits, right? The sum of two convergent series in the second one right here will just be the sum of each series individually added up. If we have a constant c times some series, we can pull that constant out and just multiply it by that sum of that series. Okay, just some tricks to have in your back pocket along the way. Okay, here's where we get to this thing we call the divergence test. Okay, all of this stuff up here is important, but it leads us to this right here. The test for divergence. The first thing you should always do when asked whether or not a series will converge. Right? So let's say we have a series from n equals 1 to infinity, and it's an infinite series of this sequence a sub n. The first thing you should always do before you test anything, before you test to see if it's geometric or start the ratio test or any other test, is you should take the limit as n goes to infinity of that sequence. Okay, if it doesn't come out to be 0, it's immediately divergent. You can stop right there. You can say series divergent. Okay, if it comes out to be 0, okay, if the limit of that sequence comes out to equal 0, all that means is that it's got a chance. It's got a chance to converge. Okay, and then we start our testing. All right, so let's get into this and jump into the ratios. Oh, sorry, we got an example. Okay, so here I've got a sequence or a series. I want to know whether or not this series will converge. Okay, it doesn't say determine what it converges to. It just says does it converge. Well, let's look at the first couple of terms. 1 squared over 5 times 1 squared plus 4, which would be 9. Okay, so I got 1/9 plus. Okay, that'll be 4 over 24. Okay, then we'd have, let's see, 9 over 45, 49, okay, etc. down the line. Okay, so does it look like maybe the limit of that sequence is 0? Potentially, right? So it might have the chance to converge. What I'm going to do before I do any testing of any sort is I'm going to take the limit as n goes to infinity of the sequence. N squared over 5n squared plus 4. Well, using what we know, we got n squared here and here, so I'm going to take the coefficients, which were 1 and 5, and divide them. So the limit of that sequence is 1/5. Because this limit is not equal to 0, because 1/5 is not equal to 0, the series from n equals 1 to infinity of that sequence is going to be divergent. Don't have to go any further. Well, it looks like it's going to 0, right? I think maybe eventually it'd get close enough to 0, right? No, it actually goes to 1/5. You can be fooled by those first few terms. So the divergence test is your first line of defense, and it just opens up the gate if it's equal to 0 to all the testing. All right, so here's the ratio test. I'm not going to go through the proof, but what the ratio tests is it tests the ratio of any term divided by the term before it as the number of terms goes to infinity. All right, and you can just thank someone that was incredible and came up with this, but if the limit as n goes to infinity of the absolute value of the next term divided by the previous term is less than 1, then it's convergent. If it's greater than 1, it's divergent. If it's equal to 1, that test isn't going to help us. So it's kind of like the geometric series where r is, the absolute value of r is between -1 and 1, right? That less than 1 value, okay? However, in the geometric piece, if it was equal to 1, it'd be divergent. Okay, but here we're looking for our limit as n goes to infinity of those two terms divided, the absolute value of them, to be less than 1. Okay, so let's try an example here. The proof here as well, if you wanted to go through it, that's fine, it's up to you. Let's go ahead and let's test to see if this series n cubed over 3 to the n from n equals 1 to infinity of n cubed over 3 to the n is convergent. Okay, so let's use the ratio test. Okay, so here we go. Using the ratio test, I want to do a sub n plus 1 over a sub n, absolute value, and take the limit as n goes to infinity. If that comes out to be less than 1, we're convergent. So let's see if it works. So let's take the limit as n goes to infinity of a sub n plus 1. Well, what would that be? That would be n plus 1 cubed over 3 to the n plus 1. That right there is a sub n plus 1. That is the n plus 1th term. Let's divide it now by the original, which was n cubed over 3 to the n. Okay, so this is one of the only times I'll actually write it out this way, but what I normally do is I write it out as multiplying by the reciprocal of the denominator immediately. Alright, so absolute value n plus 1 cubed over 3 to the n plus 1 times the reciprocal of that lower expression, which would be 3 to the n over n cubed. Okay, so something cool is going to happen here. This right here is actually 3 to the n times 3 to the first. So 3 to the n's cancel. So I get the limit as n goes to infinity, the absolute value of n plus 1 quantity cubed over 3 times n cubed. Alright, so I want you to think for a moment on the side about this. Okay, I'm going to pull out that 1/3. I'm just pulling this 3 out, putting it out as 1/3. What's going to happen to this? If I were to expand that, I'd get an n cubed plus a bunch of stuff. Down in the bottom, I'd have an n cubed. What will that limit go to? All right, this will go to 1. And therefore, the limit of all of that goes to 1/3. Is 1/3 less than 1? The answer to that is yes. Therefore, by the ratio test, not the patio test, by the ratio test, since the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to 1/3, with 1/3 being less than 1, and this is important, all terms are positive, the series from n equals 1 to infinity of a sub n, which we know from above, will converge. Okay, now that is like some nasty writing, right? It's not very clean looking, but it gets the point across. I want yours to be very clean looking. Now, do we know what the sum will be? No, we still don't know what the sum is. We just know that it's convergent. That's all that this is doing for us. It's just telling us it's convergent. All right, let's move on. All right, looks like we're on the homework. Okay, so let's take a quick look. I want to look at was it this one I wanted to look at? Nope, it was this one. Okay, cool. All right, so I wanted to look at this problem F. Okay, I'm going to take this sequence n to the nth over n factorial. Woo! Just so you know, the first clue that you should be using ratio test, if it doesn't say use ratio test, is any sort of factorial or any sort of power or exponential, or excuse me, yeah, exponential. That right there is a dead giveaway. So this is a sub n. Right? So let's take the limit and use the ratio test as n goes to infinity of a sub n, a sub n plus 1 over a sub n. So that'd be n plus 1 to the n plus 1th over n plus 1 factorial. Okay, the original, but I'm going to take the reciprocal of that, n factorial over n to the n. Okay, so now I got to do some algebra here. I'm going to take n plus 1 to the n plus 1 power and turn that into n plus 1 to the nth times n plus 1. Okay, so this term right here is going to become n plus 1 to the nth times n plus 1. Okay, n factorial I'm going to leave as is right here. That's just going to stay itself, n factorial. Down here, I'm going to take n plus 1 factorial, turn it into n plus 1 times n factorial. And I think that's all I want to do. Okay, so I'm going to leave this one as n to the nth. Now I want to do a little bit of reducing. Okay, I see an n plus 1, that's out. I see the n factorials, those are out. So I'm going to get the limit as n goes to infinity of n plus 1 to the nth over n to the nth. Now where do you go from there? Now I think the clue above was maybe a good idea of where we should go. So it says 1, limit as n goes to infinity of 1 plus 1 over n to the nth. That means I'm probably going to want to link these two together. So check it out. It's a pretty cool situation here. I'm going to take n plus 1 over n all to the nth. I can do that because both are taken to the same power, right? So I can kind of pull them out of there. All right, and then how do I turn that into 1 plus 1 over n? Well, if I were to split them and go n over n plus 1 over n to the nth, now I have here 1 plus 1 over n to the nth. And if you don't remember, actually the definition of this is the limit of that as n goes to infinity is e. Okay, and we're done. So e is definitely greater than 1. Therefore, the ratio test tells us that the original, right, the sum as n goes from 1 to infinity of n to the nth over n factorial, it is divergent. All right, let's do one more. All right, cool. Ratio test. Looking at both of these, actually, I know that the ratio test is irrelevant. How do I know that? Well, because both of these are geometric. This would be 1/2 to the nth power, right? Which would be, let's see, the first few terms would be 1/2 plus 1/4 plus 1/8, etc. So I know, how do I know it's going to be convergent? Because r is less than 1. What is r? r is 1/2. What is a? Well, it's the first term, 1/2. Therefore, I can actually find the value of this sum by taking a over 1 minus r. You might remember that from earlier this chapter. So the infinite sum is 1/2 over 1 minus 1/2, which comes out to be 1/2 over 1/2 So the infinite sum here is 1. Okay, so the first thing you should always do is see if it's geometric. Okay, let's look here. So we know this is convergent, by the way. Okay, let's look at this next sum. N equals 1 to infinity of 2 times 1/3 to the nth power. If you don't know it's geometric from just looking at it, then write out the first few terms. So the first term would be 2/3. The next term would be 2/9. The next term would be 2/27, etc. I can see that the first term is 2/3, and the common ratio is 1/3. Okay, so since r is less than 1, this will be convergent. It's a convergent series, and that infinite sum would be the first term over 1 minus the common ratio. Okay, it's total coincidence that both of these sums came out to be 1, but I'd get 2/3 over 2/3, which is 1. Okay, coincidence that they both came out to 1. That's what it is. All right, that is day number 5 on infinite series and the ratio test.